Hello, calculus fans. All right, so we've talked a bit about how the derivative tells us where a function is increasing and where it's decreasing. So let's describe a theorem now that encapsulates all of this. This is the increasing-decreasing test. And it basically says exactly what we've talked about before, which is that if the function's derivative is positive on an interval, then the function is increasing on that interval. And likewise, if the function's derivative is negative on an interval, then the function is decreasing on that interval. We've talked about this before, so this is nothing really new. Now this theorem can actually be proved from the mean value theorem, and I would suggest that you read the proof in the book to see how this is done. Let's use this now to do an example of a problem where we're going to try to calculate where a function is increasing and where it's decreasing. So let's take this function, 12x to the fifth minus 15x to the fourth minus 160x cubed plus 360x squared plus 45. Let's find out where this is increasing and where it's decreasing. Now this is one of these problems that's actually really hard to do with your calculator, because your calculator is going to have a very difficult time trying to graph this thing. So the power of calculus is really useful here. All right, what we want to do is compute a derivative so that we can use the increasing-decreasing test. Now computing the derivative is easy. We just need to use the power rule a few times, and you end up with something that looks like this: 60x to the fourth minus 60x cubed minus 480x squared plus 720x. Now I'll just go through that, double check to make sure that agrees with what you have for your derivative. And let's try to factor this thing out. What you should see is that you can pull an x out of everything, and you could also pull a 60 out of everything. Notice that every coefficient in here is divisible by 60. So if you do that, then you'll end up with this expression. Okay, now here comes the tricky part. I'd actually like to factor this a little bit more. So we're going to dig up a few things from pre-calculus. In order to factor this, we can do it by finding a root of the polynomial. This is because of the factor theorem. Every time you have a factor of a polynomial, you have a root. So instead of looking for factors, let's look for roots of this third-degree polynomial. So really, I'm focusing on factoring this piece here. Now, because of the factor theorem, we're looking for roots. And then there's another theorem that comes up in pre-calculus, and that's the rational roots theorem. It tells you what are the rational roots that you might try of a polynomial like this. Well, the factors of 12, which is the lowest order term here, you can have 1, 2, 3, and 6. And really, we should try positive and negatives. The rational roots theorem tells us those are the only possible rational roots. So all we're going to do is just try those. We're just going to try all those values until we find a root. So let's let g of x be this thing here, and we're going to apply the rational roots theorem to see if we can find a root of that thing, which will then give us a factor. Okay, so I'm going to start plugging in these values into g of x, see what we get. So if we try g of 1, you should check it out. You'll end up with 4. If you plug in negative 1, you'll end up with 18. I'm looking for 0 here. I'm looking for a root. Okay, so let's try plugging in 2. Aha! G of 2 is equal to 0. You should verify this. If you plug in 2 into this thing, you will get 0. Now there might be other roots, but at this point I don't care. Stop! The factor theorem tells us that because we found a root of this polynomial, that means we also have a factor. Since 2 is a root, that means x minus 2 is a factor. This is one of these long-lost theorems from pre-calculus. So what we need to do now is, since we know that x minus 2 is a factor of this thing, we're going to do some long division to pull out that x minus 2? Well, this is another long-lost theorem of pre-calculus, doing polynomial long division. I'm sure you've all done this before. It's not particularly exciting, but we need to do it in order to pull it off. Okay, so I won't go through all the gory details of the polynomial long division. You might want to double check to make sure that this is really what you expect to see. Okay, so after doing the long division, this is the answer here, the x squared plus x minus 6. Okay, so let's put everything back together. So in the last piece, we factor out that x squared plus x minus 6. That's easy enough to do. You just end up with x plus 3, x minus 2. And now we've got a complete factorization of the derivative. So that complete factorization looks like this. We already had the 60x out in front. We used the rational roots theorem together with the factor theorem to determine that x minus 2 was a factor. And then we pieced together two more factors that we got out of the quotient once we divided. So we've got x minus 2 twice. You should see that because it was one of the factors here and then it cropped up again. And then we have x plus 3 as another factor. All right, so that's a lot of work to get a factorization of the derivative, but it's really very important. We want to be able to have a complete factorization of the derivative. We'll see that in the next stage of the problem. So at this point, we've got three critical numbers. X equals -3, x equals 2, and x equals 0. That just comes from setting the derivative equal to 0. Those are the numbers that will make the derivative equal to 0. Okay, since we have the three critical numbers, what we'll do now is create a sign chart to show what happens in various intervals between the critical numbers. Now, I'd like to just set up a sign chart before we fill it in. So the sign chart is going to look something like this. Okay, so the rows are going to be the various intervals that are between the critical numbers. So we have to go from -infinity to -3, to -3 to 0, 0 to 2, 2 to infinity. So those are the intervals between and outside of the critical numbers. Then in the columns, what we have are the various pieces of the derivative. So remember, we have a fully factored form of the derivative that looks like this. And so the columns that we have in the sign chart are going to be these three pieces that we're multiplying together. So that's the 60x, the x minus 2 squared, and the x plus 3. Those are the columns that we're going to have in the sign chart. Now all we're going to be putting into this sign chart is positives and negatives. Now I'm just going to do a couple of examples so that we can see what's going on. So let's take this entry here and decide whether or not it's going to be a positive or a negative. So what we're going to do is just pick sample points on each interval and use that to plug into each piece to determine if it's positive or negative. Now once we have the table all put together, that's going to tell us whether f prime is positive or negative, which in turn tells us whether the function is increasing or decreasing. Okay, so again, let's see what's happening here. So our test number that we want to plug in is any number between -infinity and -3. So if we plugged in, let's say, -4, that's on that interval, and we plugged it into this expression, we would get a negative number. So when filling out the table, we would put a negative sign here. Now let's fill out this piece here. That's going to be a positive number because we're squaring what's on the inside. So it doesn't even matter what we plug in. So at this point, the table has to look something like this. Okay, so what you should do is go ahead and choose those sample points and plug values in and see if you get positive or negative numbers. And it's very important to understand, you don't care what the number is. What you care about is it positive or is it negative? So let's look at the filled-in chart. So the filled-in chart looks like this. After you've decided on positives or negatives, then, for instance, this is gotten by saying, well, we multiply these numbers together. And if we multiply two negatives and a positive, then we're going to get a positive number. I don't care what positive number, I just care that it's a positive number. And you do that across each row to determine whether the derivative is positive or negative. Having determined whether the derivative is positive or negative, now that allows us to transition to saying what the original function is doing. When the derivative is positive, that means the original function is increasing. When the derivative is negative, that tells us the original function is decreasing. Okay, we've got our final answer now. The original function is going to be increasing here, and so we'll just take those intervals and piece them together. It's increasing from minus infinity to minus 3, 0 to 2, and 2 to infinity. And then it's decreasing only here from negative 3 to 0. So this is going to take a little bit of work on your part to just double check to make sure that the table is really filled in correctly. Okay, that's all for now.